Today we'll be talking about nuclear chemistry. Well, nuclear chemistry deals with the nucleus of an atom. Unlike chemical bonding, which deals with the electrons in the valence shell, the nucleus is made up of protons and neutrons. It is what makes an element an element. So note, though the nucleus is positively charged, it does not have the same effect as magnets, because when you put two magnets together, they usually, that are the same, like positively charged, they pull away from each other. They don't want to come together. But because of nuclear force, which is the exchange of mesons, it keeps the nucleus together. So as long as the protons are constantly exchanging mesons, electromagnetic force can't take over and pull the nucleons apart. So now that we know this, let's move on to what radioactivity is. Radioactivity is the process of a nuclei decaying and emitting matter and or energy. Most nuclei are usually radioactive when there are about 83 protons or more. So an example of what radioactivity looks like when those particles are being emitted is like when you cut an apple. When you cut an apple, usually juice comes out. The juice would be the radioactivity coming out. It would be that matter and that energy. So when a nuclei becomes extremely big with many protons and neutrons, the nucleus becomes unstable and splits, emitting radiation. Though a nucleus is considered stable, you have to understand that though a nucleus can only be considered stable if nuclear force can keep the nucleus permanently together. If there's any chance of it being able to split it, then it's considered unstable. So next we're going to talk about the different kinds of radiation. Okay, so there are three types of radiation. There's the alpha radiation, the beta radiation, and the gamma radiation. So I talked about how matter and energy are what is emitted during a radioactive decay. So alpha and beta radiation is matter, and the only energy or that is going to be the gamma radiation, which is electromagnetic waves. So alpha radiation is when two protons and two neutrons are emitted. They're gone. They've been whooshed away in a reaction or in a decay. So alpha radiation is represented by this symbol. It's a little squiggle. I'll write another one. Really big. It looks like this, and that's how you know you have an alpha decay. The atoms are really big, and it doesn't take a lot to get them to get stopped. It can be stopped by a piece of paper. So they're very slow, and they have the least penetration power of the three kinds of radiation. So here's an example of an alpha decay. So Ba has 139 neutrons and protons. It's the atomic mass. And when it decays, it becomes Zion, which has 135 in total because two protons and two neutrons have left the nucleus. Okay, so next is our beta radiation. It's expressed by a big V with like a P almost, P line, and a negative up top. These particles are 7,000 times smaller than alpha particles. They result in a high energy loss of an electron and a gaining of a proton. The neutron decays into a proton. This only happens when the ratio of protons to neutrons is too high, and the penetration power, you would need 3 millimeters of aluminum to stop it. So an example of this would be FR is 87 protons, and it has 213 total of protons and neutrons. So when a beta reaction occurs, you gain a proton, and then so your mass doesn't change here. But you do, when you look at it, you do lose a neutron. The neutron decays into the proton, and you lose an electron. Okay, our final one is gamma radiation. Gamma radiation are extremely high energy electromagnetic waves. It's represented by this symbol, which kind of looks like an 8 that's missing a piece out of it, or an infinity sign, whatever you'd like to see it as. It has almost no mass, and it has no charge. It travels at the speed of light. It's usually emitted from a nucleus during an alpha or a beta decay. When it occurs, the nucleus loses energy, and you would need lead bricks or extremely heavy objects to stop this kind of radiation. And so then here also is what a neutron decay looks like. It would be a neutron, and it would either emit a proton, an electron, or here it's like a little V and an E, and is what's given off during a neutron decay, when a neutron decays into a proton and a beta particle. So the next step in nuclear chemistry is going to be transmutation. Transmutation is the process of changing one element to a different element. So that means you're manipulating the protons pretty much. So some nuclear decay results in transmutation. So that's any kind of beta decay, alpha decay. So a half-life is the amount of time it takes for half of the nuclei in the sample of an isotope to decay. It does not matter, it's random, it's a random event, it doesn't have an order like every 5 years, a fourth of it's going to decay. It's half the life of a particle, a particular element is the same no matter how much of you have it. So if you have 100 grams, 50 grams, 2 grams, the half-life will remain the same. If it takes 1,000 years, then all of those will take 1,000 years to get half of it. It does not decide that, so that means it just doesn't depend on the size. Here's an example. So if you have 100 grams and you give it 1,000 years, it's 1,000 years for this particular element, then it will have 50 grams. So this would be called the daughter nucleus, and so then if you gave it another 1,000 years, it would result in 25 grams. If we come over here, flip it. The amount of time is a matter of it depends on the substance. So for PO, it takes less than 1,000th of a second for it to result in its half-life. But if you look over here, carbon-14, it takes 6,000 years. 6,000 years. And if you look at U, it takes 4.5 billion years. So each element has its own time frame it takes for it to become a half-life. So here's an example of a half-life problem in which you would use it. It says the sample of polonium-214 originally has 1 gram. Express the mass of the remaining as a percent of the original sample after a period of 1, 2, and 3 half-lives. Approximate how much time has elapsed when 20% of the original sample remains. So how you would solve this, well, you know, 1/2 times 1, because it's only 1 half-life for the first one, would result in 0.5 grams. Well, if you put that into a percent, which you'd multiply by 100, you'd get 50% remains. Now you have 2. Well, 2 half-lives, you put 2 to the half, is 0.25 grams. So that results in 25% remaining. And then again, you do it with the 3, and that you get 12.5% remaining. So if you approximate that, you can kind of go around and figure out how much it would take to get 20%. You have to kind of play around with your numbers, and that would be approximately 2.32 half-lives to have it get around 25%. Well, and how you can be sure is you know it's going to be greater than 2, but you know it's going to be less than 3 half-lives because of these two numbers you have here. Next, we will do some more problems revolving around the alpha decay and the beta decay. Okay, so here are some alpha and beta decay equations, problems, whatever you'd like to call them. So we're first going to take an alpha decay problem, which is BA. So remember that an alpha decay problem it's losing 2 protons and 2 neutrons. This is going to change the atomic number and the proton count. So you're going to take BA, and that's going to become xeno, because you're changing the element. You're changing the element completely. And then the atomic number changes to 135, and here's your little sign that here's where all your protons and your neutrons left. So then here is a beta decay problem. This is where you're going to gain a proton because a neutron decays into the proton, and you're going to lose an electron. So here you go, here's your proton count. Though your atomic number does not change, you need to realize that the proton and neutron ratio does, because your protons end up going higher and your neutrons lose 1. So here's an example where iron changes into Ra. So you're going to get an 87, it becomes 88. But here's your count, your neutron and your proton count. Okay, so now we're going to move on to a more complex problem where it's going to be a 2-step beta and alpha decay problem. Okay, so here's an example of a 2-step problem. You have your original element that's going to have an alpha decay. This is your alpha decay right here. And then it's going to go, that's going to be your A. element because they're not giving you it, and then it's going to have a beta decay, which is then going to give you your B element. You have to go through and you have to balance the equations to be sure that you're getting the right elements, because the minute you screw up your balanced equations, it's no longer right. So when bismuth changes into, it has an alpha decay, it's going to result in thallium, and so then thallium, here's your balanced equation, and then thallium becomes your A element, and it's going to have a beta decay. The beta decay is going to add 1 proton. In an alpha decay, you're going to lose 2 protons. So this becomes 82. This is your balanced equation, and that becomes lead. So your final element becomes lead. You had to do a multi-step problem using both your alpha and your beta decay problems. Thanks for listening. I hope you enjoyed learning about nuclear chemistry.